What's up, everybody? Welcome to an extra lesson. So, I give extra lessons now, right? It's amazing. Anyway, this is how to read a periodic table, and it's really important because and you don't have to necessarily do this. You don't necessarily have to go back do this at the end of lesson 2, even though it's called 2.x. It's really just an extra lesson. But you don't have to go and look at this after lesson 2. In fact, you won't understand many of the things I'm going to say regarding this in lesson 2. So make sure you watch a good amount of the chemistry videos before you go back to this lesson. I'd say at least chapter 8, for the future people. Right now I don't have chapter 8 released yet. For chapter 8 and chapter 5 will tell you most of these mean, right? So like the atomic mass and stuff. So anyways, today we will be analyzing the periodic table. So what's the periodic table, right? I will take hydrogen, for example. So I'm going to draw hydrogen big right here. Hydrogen 1, and it has the name hydrogen, and it has the atomic mass 1.01. I'm sorry, this is really bad. So hydrogen 1.01, 1. But first of all, this is the atomic number of the, I forgot to put atomic number here. That's how bad I am. Right? This is the atomic number of the atom. So that signifies how many protons it has, right? Normally it also signifies how many electrons it has. So one atom, 1 electron and 1 proton is what a hydrogen atom has. This is its atomic, okay, I'm gonna circle it with another color. Let's do red. So this is its atomic symbol, right? I'm gonna put 0 atomic number, right? This is its atomic number, has its atomic symbol, and the name of the atom is down here. So if you read, let's say CR, for example, that's chromium, right? Or Mn, I think Mn is an atom, manganese, yeah, manganese. Or Am is americium, right? Now, let's use green for atomic mass. That's its atomic mass. Right here is atomic mass of selenium, 78.97. Atomic mass of carbon is about 12.01. Atomic mass of fluorine is 19. Atomic mass of lanthanum is 138.91. Right? We keep counting. So, it's organized pretty cool, right? Why is there a huge gap here? Well, I'll tell you later why there's a huge gap. Well, this is one of the reasons why. This is actually one of the reasons why there's a huge gap. So types of elements belong to all of this down right here. So alkaline metal, alkaline earth, transition metal, basic metal, metalloid, and all of these stuff. And in fact, if you finished chemistry, you might not even understand what they all mean. For example, I don't understand what alkaline earth means. They are alkali metals, so they do react relatively strong with these type of metals, which is called a halogen. So the only thing that you really need to know is metals. These are metals right here, transition metals. These are basic metals. So these are all metals, basically. And the transition metals, what they have extra is, I'll tell you, in the electrons, they actually have a d orbital, right? So if we say s orbital and p orbital, they have an extra. No, not only these guys have a d orbital. So I need to change it to like yellow or something. Okay, only this guy has a d d orbital. Right? Only them. Only these. D orbital for them. The rest don't have a d orbital. But they're all metals, right? These are all metals. Now metalloids, like silicon, have properties that are like metals, but also not like metals. For example, silicon doesn't have, silicon's shiny, but silicon isn't, silicon's, an insulator, I think. It's not a conductor. So silicon's shiny, like metal, but it doesn't conduct, unlike metal. So, metalloids are half metals, basically. That's what I call them. But okay, so the next is non-metal. Non-metal is not a metal. We already discussed all of it. Carbon, nitrogen, oxygen, phosphorus, sulfur, and selenium are non-metals, and they're normally gas at room temperature, right? So now we have let's analyze the noble gases. Noble gases are reactive. They are pretty reactive against water. If you've seen those no metals in water, if you've seen those metals in water videos, you'll know that these are pretty reactive, right? You've never seen francium before because it's too expensive to make one, but they react with water. They also react really violently with these guys right here. Let's use green. No. Let's use pink actually. So these guys react violently with these guys, right? Why? Because this needs, recall back the ionic compounds. This needs one electron, and this gives away an electron, and this takes in an electron, right? So the charge would be a 1 plus here and a 1 minus here. So these react really aggressively. They really want to take that electron, and they really want to give that electron. So it's kind of like just I don't even know. But the electron transfer is pretty violent, and a lot of energy is released, right? All atoms want to get to the 0. No, atoms cannot combine to each other to make new atoms. No, that doesn't work. But all atoms that are in this 0 period, in period 18, are stable. They're really stable. For example, helium reacts with pretty much nothing. Neon also pretty much reacts with nothing. Most of these atoms right here react with pretty much nothing because they are stable, right? They don't need to react with anything. They're already in the lowest energy state. So that's cool, right? And then we got our skipperoonies, right? We have skipperoonies right here. We have our lanthanides, which skip to here, and actinides, which skip to here. And these have something even more special called the f orbital. F orbital. And the f orbital, well, it does stuff. Okay. It's basically just an extra orbital where electrons, you can find probabilities of electrons. It's really complicated, and because I've already introduced an f orbital and d orbital for electrons, why not just introduce s orbitals and p orbitals as well? So the s orbitals are in the s orbitals are here. These are these are s, right? S, and this is s, right? Only helium. Helium is s. Helium is s. The rest are these are s. These are all s, right? But these are p. And the group numbers are 1, 2, 3, 4, 5, 6, 7. We kind of skipped, right? Anyways, the group numbers right here are 1, 2, 3, 4, 5, 6, 7. Right? There are 1, 2, 3, 4, 5, 6, 7. So the way you write the atom is, for example, if you got magnesium, you can write the orbital as either neon, so bracket like this with neon, which means neon configuration of atoms, and then you can write the orbital, which is s, and then you can write the number, the group number, which is 3, so 3s, and then you can write the number of atoms, which is 2, so it'll be 3s2 right here. Or you can write it out the whole thing. So you start with hydrogen, it'll be hydrogen and helium, they're both s, so it'll be 1s2, which is kind of counterintuitive if you're taking like algebra or something, right? Because you would expect it to be 2s1, right? But it's not, it's 1s2. So 1s2, and then 2s2, right? And then there's 6p electrons, so 2p6, and then 3s2, and that's the electron configuration of magnesium. If you want to find the electron configuration of holmium, for example, you have to write a whole lot to find the holmium. So holmium, we know it's in the lanthanides, so we can just put Xe, and then well, this is our period 6, so 6s. No, not 6s. I mean no, wait, is it 6s? Yeah, it is 6s2, and then we didn't get through the d electrons yet, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 1d1, because no, 6d1, because there's still a d electron in all of the f orbitals, 6d1, and it moves to holmium, which is 11f, no, 6f11, right? This is confusing stuff. You will understand it when you get to the electrons, right? I might actually have this wrong because I haven't actually gone to the electrons yet. There might not be a D here, but I'm pretty certain of the 6s2 and the 6f11. So that's it for electrons. Periods. So you normally would call these period 1, period 2, period 3, period 4, 5, 6, 7, 8, 13. Yeah, so there are these numbers up here. Those are the periods, right? These numbers, periods, right there, they're the periods. And people normally associate period 1 with alkali metals, period 18 with noble gases, period 16 with nothing, period 17 with halogens, period 2 with alkaline earth, period 3 to 12 with transition metals, right? So that's how you can organize using periods. And group numbers, I already told you, is basically the amount of shells. And what order does it all go? I don't even know what I mean by that. Anyways, this order right here was actually influenced by a chemist. I don't remember his name. I think it was Mendeleev. But he made the periodic table. A chemist made the periodic table of elements, and he actually made the correct model in the first try, which was really impressive. Because remember the atom models, they had to trial and error many times in order to get the correct atom model. But this guy made the correct periodic table organization pretty much on the first try, so he was amazing. But it basically goes on orders of it goes in orders of electrons, and it goes it's sorted in the amount of electrons, basically, is and it's also sorted in energy. And you could actually see that if you've watched my electronegativity video, it's also kind of sorted in electronegativity, where the more to the right you are, the more electronegative your thing is. Right, so fluorine has a 4.0 electronegativity, which is amazing. But then when you go down, tennessine only has, I think, like a 2 electronegativity. So they're more likely to form ionic bonds with higher group numbers that are higher, right? So group 2 or group 3. Radioactivity. So all atoms after uranium are radioactive, and they become radioactive quicker and quicker. they're like radioactive enough so that they don't even they're not even able to exist for a few seconds, and they have no stable isotopes. So that's basically what there is about radioactivity. I might update this video, but for now that's gonna be it. I might update this video in the future if I find more periodic table trends that I guess are unique and good to discuss. I could talk about the ionics and the 1, 2, 3, 4, 5, 6, 7, 8 valence electrons, but I already covered all of those um, in the other chapters. So that's gonna be it for today, and I will see you next time for I think it's electron activity.